below Atlas. And I'll start by going into the Cohort Method R package, and then I'll review the code that actually was generated by Jamie when he pushed that button and said download. So the Cohort method is an R package that is freely available. It's on GitHub, so you can just go to the OHDSI GitHub and look for Cohort method. And what you'll find is on that first page, when you go to that repository, you'll find instructions for how to install the package. You'll find a package manual that basically describes for every function that is in the package how to use it. And there are also two so-called vignettes, which are basically longer documents that describe step by step how you would use this Cohort method package. So what is the Cohort method package? So basically it is a library of R commands, just commands that you can call and apply to something. And what it allows you to do is to, with a few lines of code, implement a full cohort study. And because you're at that point in R, you're actually very flexible in what you can do. So it has functions for example, matching on propensity scores, but if you don't like the kind of matching that it does greedy matching, and you want to replace that with some other matching, well, just go ahead and write your own R function for the kind of matching that you want to do. But that does require, of course, that you're familiar with R. The Cohort method package talks directly to the database in the common data model. So it's not that you first have to extract some sort of a analytic data set and then you apply the Cohort method package. No, you just point it to where the common data model lives. It talks to the database and it extracts all the data that you need for you. What it is not is it doesn't have a point and click interface. That's why we built the one you just saw in Atlas. However, of course, not all the functionality that you have in the package can be made available through the point and click interface that we have in Atlas. So there's actually more stuff you can do in R than you can do in the point and click interface. And especially this functionality that I mentioned earlier, that of course something you would have to do in R. What is also important to realize is that the T, the C, the O cohort that you need, you can't construct them in Cohort method. You need to already have constructed them somewhere else, for example in Atlas, and then you can point the Cohort method package to basically a table that holds them for you. However, you can actually construct your T's, C's, and O's that you defined in Atlas in R, but I'll get back to that later on. The one thing that's maybe a little bit complicated, but that is important to understand, is that in Cohort method we define two layers of working with this package. The first layer I'll refer to as the single study, and the second one is the multiple analysis. Both of these are actually described in their own respective vignettes that come with the package. So in what I will call the single studies approach is more the basic way in which you use R. So you call a certain function, like the getDB cohort method data function, which has a bunch of parameters that I'm not showing here. What that function does is that is the only function that actually talks to the database. And that gets you all the data that you need for your study, the T's, the C's, the O's, the covariates, and everything. And it stores all of that in an object that we'll call CMData. And then there's another function that you can call on that, create study population with, again, a whole bunch of arguments I'll not go into. And it requires that CMData object that you generated earlier. And basically at this point, you would create what some would say the analytic data set. So here's where you define your time at risk, which outcome you're actually interested in, whether you want to exclude people with the outcome prior, etc. So you get another object, study pop. You then feed that into another function, say create PS, which creates the propensity score. It has a bunch of arguments, but basically it uses that population that you just defined and fits a propensity model. You can say, oh, I want to match on that. Call another function, match on PS, and then you, once you've matched on the propensity score, in this case, you can call another function, say fit outcome model, and that will fit the actual model, for example, a Cox model. And if you inspect that last object, that will tell you what the hazard ratio is that you're trying to estimate. And actually, this is exactly how you would perform a study with, at the very minimum, or you can leave some of them out, but typically you have like 5 commands, and that would lead you to complete the entire study. And so it has a sort of a linear flow where you just take one object from to the next. But as we already shown you a little bit, often what you want is you don't want to just do that for one TCO, you want to do that for multiple TCOs, here still referred to as drug compared outcomes, but TCOs, and you might have different analysis settings. You might have a primary analysis where you do matching, and then you want to do some sensitivity analysis with stratification or different time at risk windows. So you have multiple TCOs, multiple analyses, and then you probably want to just do the full product for every TCO you want to use, every analysis setting. And so especially when you start to include, say, 100 negative control outcomes, that's quite a lot of TCOs that you want to run. And sure enough, that first approach that I showed you, you can just put that in a for loop and just run it over all the TCOs and all the analysis. But that's not very efficient, and it's also not very pretty code. And so that's why we created this second layer, which I call the multiple analysis layer. So instead of calling all of these individual functions on an object, what you do is you specify the arguments which should be used to call those functions. So instead of calling getDB cohort method data args, you call the function create getDB cohort method data args. So you create a object that has nothing else but just the arguments with which the package will later on call this this function. And you do that for all the functions that need to be called, and then you can combine all of those into a single unit that we call an analysis. And so I can give that analysis an ID, in this case analysis ID 1, and I can even give it a description. I'll just call this one one-on-one matching. And now I've defined an analysis object. And I can feed that into the package, and then it knows, oh, I'll just need to apply this analysis to every TCO that you define in another object. The reason why I have to tell you about this level of complexity of the package, and not just stick to that first level, is that what Atlas does is it skips that part of it and actually produces directly the analysis object that you would otherwise generate using these R commands. Yep, go ahead.
The single analysis object or the multiple, or both?
So only the multiple analysis one has this notion of an analysis object that fully specifies the analysis. Otherwise, you'd just be calling commands with arguments, and you'd actually nowhere have a real, just an object that defines the analysis. Except
bundles the multiple for you.
Yeah, but it's just a specification. It's not actual code. It's just, and actually we save that as a JSON object. Which is to say that what you'll see in the package that is generated by Atlas is you'll just see this analysis object, and just to demystify what that is just a thing that you could also generate it with a bunch of R code. All right, what I'll do is I'll now go over how you would implement the Graham study just using that first layer, the single study layer. And once you get a hang of how that works, it will be easier to understand what actually is happening in the package that we created in Atlas. So step one is we have to get all the necessary data from the database. That means we need to get the targeted comparator cohort of interest, both the index dates and the end of the cohort date. We also need to get the end of observation. We need to get the outcomes of interest, including the dates of occurrences, and the covariates. So those T's, C's, and O's, like I already mentioned, they're not actually constructed by the Cohort Method package. It assumes they already exist in the database somewhere in a table. Could be in, like the common data model has a table called cohort, and like it assumes it is in a table that has at least that structure. It doesn't have to be specifically that cohort table. And a bunch of covariates. So Graham used several covariates. We already discussed this actually. I'm not going to do what they just, so this is actually, sorry, this is some old code where we try to reproduce exactly what they did. What we need to do is we need to create a bunch of, basically another settings object that just defines which covariates Cohort method should construct. And so we use this function called create covariate settings, and that just allows you to turn a lot of things onto arguments to true if you want those, like demographics for gender, age, and whatnot. And then you call the function I also mentioned earlier, getDB Cohort method data. And so when you call this function, you need to point it to the T, C, and O cohort. So you have to tell it, well, my exposures live in a table called cohort. Outcomes, by accident or happen to also live in that same table. And they all have their own IDs, which we'll call now the target ID, the comparator ID, and the outcome IDs. I also here provided that settings of which covariates to construct. And in the top, you'll see I need to provide it connection details, which basically tells you how to connect to the database, like the server name, your username, and your password. And you need to tell it which schema holds your CDM data. So that object that is created, the Cohort method data object, can potentially be a very large object. But we're using a feature of R called FF that actually allows you to store very large data objects, including ones that wouldn't even fit in your memory. It will just use memory mapping with your hard disk to make sure that all of that you can just hold in R. That does mean that you can't just call save RDS or the save command in R that you normally would use to store an object. You need to use this, this function save cohort method data to store it on the disk if you want to save it for later, which you probably want because remember what we're doing here is we're loading the data about your T, loading the data about your C, loading the data about your O. That's probably not so big. But then we're constructing all of these covariates, and like I said, somewhere between 10,000 and 100,000 covariates is not out of the ordinary that you would see those being constructed. And so this can sometimes be gigabytes of data that you're pulling from the server. You can, of course, just inspect this data. So in R, you have these generic functions like summary, and you can just call summary and cohort method data. And in this case, it will tell you what the T, C, and O is that you extracted, how many people there are in there, and how many times the outcome was observed. It also tells you in this case there was a very small set of covariates constructed, but there were still quite a lot of non-zero values for those covariates observed. All right, so the next step that we need to go through is once we have the data, we have to create the study population. And so the arguments that you see here are like what should be the risk window start, what should be the risk window end, and how do you define that relative to the start and end of the cohort. They're actually very similar or exactly the same as the options that Jamie showed you in the Atlas interface. And that's, of course, not a coincidence. We designed it that way. The Atlas interface is just a point-and-click interface that allows you to specify these options. And so again, here you can specify whether you want to remove people that had the outcome prior and what the look-back window is. The next step is to create a propensity model. And we can actually be very brief about that because there's not much to specify here. If you just use the default options, typically that is good enough. So you point it to your cohort method data object because that's where the covariates are stored. You point it to the study population object that we just generated, the people that will be in your study. What happens when you call this function can be quite complex because now we want to fit a regularized regression on 100,000 variables for maybe 500,000 people. So even though it's just one line of code or two, this can take quite a while. But it's all fully automatic, so you don't actually have to think about it. it uses cross-validation to pick the right hyperparameter and stuff like that. So this can really take a long time to compute. There are some options. Well, I'm not going to go in there. You can actually set it to use multiple threads, but that's we'll get to that later. And of course, once you've done that, you probably want to save that because you don't want to do that again. So now that we've done that, we might want to see what the propensity score distribution looks like. And so we can just call the plot PS function in the Cohort method package. We just aim that at that PS object we just generated, and we get this plot that we can inspect. So we can also save the plot to disk. There's an argument file name that you can specify, and it will save it to disk, and you can put it in your paper if you want. In this case, so what do we think of this propensity score distribution? Looks nice, huh? Yeah. So these people are actually fairly comparable to begin with, because the propensity model doesn't really know how to distinguish between the two groups. There's a large amount of overlap. But still, we want to probably match on that to get rid of some of the differences that are still visible. So the next step is to match. So we call the function match on PS. There's of course also a function stratify on PS. But in this case, we apply that to the PS object, and one of the options we have is to define the caliper. So the caliper is the maximum distance that we allow between two people to have them matched. So in this case, I think Graham explicitly states that they used a caliper of 0.25 on the standardized scale. They definitely said in the article that they were using one-on-one matching. So we set the max ratio to 1. That means that for every person in the target cohort, we're selecting one, or at most one person in the comparator cohort. If there is nobody within the caliper in the comparator cohort, then we don't have a match, and we basically throw away that target person. So it's certainly the case that we can lose a lot of people here. Also, there could be a lot of people in the comparator cohort that never get matched to anybody in the target group. Yep.
Could you go back to the previous slide? So this is like the question I was asking you in the hall. If where the red and blue intersect, if you drew a line down from there and went somewhat to the left, you would get a lot more overlap, it seems like, than if you go to the right. It seems as, but that's, Attrition is the red.
Yeah, so this is your target cohort, and matching is actually hardly ever symmetrical. Okay. So it depends, here it actually starts to matter which one is your target and which one is your comparator.
Right.
So in this case, if we say dependency is our target and we want to do one-on-one matching, well, so this is a distribution, of course. It just tells you how many people there are at various points. And so here there are a lot of people in the target group, in the dependency group. And so for every one of those, we have to pick a comparator. But you can already see, because we're not reusing comparators. So here there are a lot more people that are on the target drug than on the comparator drug. So that means that at this stage, for some of them I will find a match, but then the match is gone, and so the other ones are left in the dark, and I don't have anyone to compare it to. And then here, the opposite is true. So for everyone in the target group, there are lots of people in the comparator group that I can use, but I specified I only want to use one, so all the other ones in the comparator group I'll lose.
But I guess my question is more, if you say, go to the red area that doesn't have any blue in it, especially maybe that area at the top, or are you going to end up with people who are really quite different from the people who are in the intersection area?
Yes. Yeah. No. Actually, it is exactly the intersection. Let me see if I actually plot that somewhere.
Oh, right.
So you can actually also plot what the propensity score distribution is after matching, and it depends a little bit on how the distribution is and actually what the absolute numbers are. But you get something that is a little bit close to the actual intersection of this. That's what's left.
Okay.
We usually don't use one-on-one matching because you're just throwing away people. So at the very least, do variable ratio matching, where for every person in the target group, you're allowing, well, we typically say up to 100, but we never reach that, allowing as many comparators as you want. So that means that here you're still in trouble, because for every target person, there is not enough comparator persons. But here it means that for every target person, you can use quite a lot of comparator people. So we typically use variable ratio matching when we use matching. And we actually prefer stratification, because then you don't lose anybody. But if you do stratification, it might be that your strata is too big and you actually still have residual differences. So it's a trade-off.
Martin? Yeah, hi.
Go ahead, yeah.
I remember there was one, they came to J&J presenting one colleague from Duke University. He used 500 strata. That computationally take more time. But he actually showed, he said, if you use the 5 quintiles, there's a residual confounding. So he used 500 during his presentation at the J&J while he was given. And I was thinking, while I was looking at, we use 10. So what's the restriction? Is that getting more and more is better, or computationally prohibited?
So it's not, computationally it doesn't really make a difference.
Okay.
However, if you're doing 500 strata, that's getting very close to just doing matching, I would say. I don't know. I actually never done 500 strata. Maybe it's a good idea. Now that you mention it, I can't think of a reason why it would be bad, but...
Yeah, he showed his presentation, he showed it. But he only showed 5, he didn't show 10, another one. He showed 5, there's a residual confounding imbalance when you do the stratification, not do matching.
So you do 5 and 500?
Yeah, 5 strata basically.
I bet 10 is probably pretty good.
Well, I don't know.
5 was bad.
I don't know, but he showed the differences. That's why he said he do 500, and then he showed that the residual is
yeah, me, I personally like to use 10 strata, but and so I don't have. I do actually have some evidence to back that up. Is I use negative and positive controls, and I see that they actually address bias, and I look at balance, and I see that they address bias. So I think that's the metrics that you should use. What specific setting you choose should mostly be driven by what it looks like in your diagnostics.
Can I ask one question? If you go back one slide. Yes, this one. Do you have any criteria that say, okay, the overlay area, the percentage of overlay, what percentage looks, kind of higher or below what percentage is not? So do you have this kind of criteria?
So Alec Walker actually wrote a paper on that subject, and he proposed a rule of thumb. And to explain the rule of thumb, I actually have to point out that what is on the x-axis is not the propensity score, but it's the preference score, which is an invention by Alec Walker in that specific paper. The preference score, so the propensity score distribution can look really weird if one cohort is a lot bigger than the other. If your target cohort is, say, 10 times as big as your comparator cohort, then the whole distribution gets a bit skewed to one side, and it's very hard to see what's going on. And so all the preference score does is it basically adjusts for the imbalance between the groups, and therefore it makes that every plot looks pretty much the same in scale.
The same area in the two distributions?
Yes. So it's not and basically it's telling you anything that's in the middle is not really that you have a 50-50% chance of getting one treatment or the other. It says you're at baseline probability. So if one treatment is 10 times more likely, then you're actually, when you're in the middle, you're 10 times more likely still to get one treatment over the other, just because that is the baseline rate that you've observed. But anyway, the reason why I'm going there is that on the preference score scale, the Alec Walker heuristic is you have to have 50% of your population between 0.25 and 0.75. So that is the heuristic. Whether that is any good, I don't know. I don't think Alec provided any good justification to back that up. But it is a heuristic that you can use. And you can say, well, if I don't meet that criteria, I decide that my two populations are not comparable enough and I have to stop this study, which is a thing you don't see happen very often, that people say, I can't do this study, but they should say that more often.
So in one matching, we wouldn't run into an issue. If you suspect there's a potential effect modifier based on propensity score, variable matching and stratification, because you preserve almost the entire sample, if it is the effect modifier, for example, if the treatment effect is bigger on the propensity on the lower, on the warfarin side, and they're getting smaller on the other side, since we don't really test that effect modifier, is that the negative control will tell us whether there is a potential that, or that won't tell you. So what happens if there is a potential effect modifier in that situation?
Well, so we're computing an average treatment effect, which means across the entire population. If there are subgroups where the effect is different, then you're basically computing an average. If you're doing stratification, that means that within each strata you might have a different effect, but you're averaging over that, so you're still good. But you're right, if you're doing so the thing with specifically matching is that you're changing the population that you're looking at. So it could be that you started off with a very diverse population of both men and women, for example, and then after stratification you only have women left. You're actually answering a different question than you thought you started out answering it. And so if there is some sort of an interaction going on with gender, then you suddenly can't look at that anymore because you're only left with one group. So that's an important thing to keep in mind, that your propensity score adjustment is specifically matching changes your population and might actually lead to answer a different question than you started out with.
Just to see if I'm understanding this right, with the Alec Walker rule of thumb, with the 50% between, it would be impossible, I guess, to have a valley that's in between 25 and, I mean, I know you can have valleys with the things pushed out to the
You can have valleys anyway.
So can you have a really narrow valley that's still left 50% in between 25 and 75?
Yeah.
Oh, and that would still be, so
okay.
even though you got no overlap, you got 50%
That's
in that range.
Well, not sure whether that would really work. I've never certainly seen that. I don't know whether it would be mathematically impossible, but
if it's possible.
I'm not sure because you have to.
So maybe the nature of the graph that if you're going to have that kind of valley, you would have to push the other things out farther. It would have to be a wider valley.
I'm suspecting that's the case, but I just don't know. Sorry, but I certainly haven't seen it.
I think part of the reason for this 50% heuristic is to try to balance the desire to get good. So you want good balance between your people, but if you throw away too many people, you're answering a different question, and that 50% is just this number to sort of try to balance these two competing interests. So you really want to make the comparison between comparable people, but if you throw everyone else away, you're answering a different question. So 50% is just this like silly number that's meant to be some cutoff where you've stopped trading off balance for the original population.
Right, but what I'm asking, I think if you've got that 50% there, what's in that 50% is a peak, not a valley.
Yeah, but
sometimes they're like kind of flat, and then there's 50% in the middle. But I haven't seen the complete separation or serious separation with 50%.
But don't get too hung up on Alex's heuristic, because what I would recommend you do is you look at your covariate balance, and if you included negative and or positive controls, you look at those, and that decides whether or not you've got a good comparison. That's more for lazy people that only want to fit a propensity model and don't want to do all the other work. So Graham didn't mention the caliper, but you should use a caliper because you don't want to allow too large a difference between target and comparator. So this is the point where we're actually at the population that's going to go into our outcome model. And so at this point we could actually say, well, I want to see how I got there in terms of numbers. And so there is a function called draw attrition diagram that I can call on this matched population that I just defined. And then you see, well, I start with my original cohorts, I lose a bunch of people because I said you can't have the outcome before the index date. I lost some people, not many, because I said you really have to have at least 1 day at risk. And I lost quite a large number of people, especially in the comparator group, because I matched one-on-one. And as I was saying, there were a lot of people there that I could have used in the comparator group. We go all the way to the left there. There were a lot of people here that in the comparator group that never get used just because there are not enough people in the target group to do one-on-one matching. And so I'm left with the numbers at the bottom. What is important to realize here is that because the T, C's, and O's are defined outside of cohort method, it doesn't know anything about that. So the numbers that you have here is the numbers that were observed in that cohort table. And so you actually have another piece of attrition that's above this, which is what happened in Atlas. So we started with the people that have the drug, and then we started throwing away people that didn't have enough observation or had to have an atrial fibrillation, etc. So there's actually a part above this. If you want to use it in the paper, you probably want to attach that above. As I mentioned before, an important metric or diagnostic that we want to use is where we want to look at covariate balance. And so the way that pretty much anybody looks at covariant balance is we compute the standardized difference of the mean. So that's basically, you compute the means of both groups, and because most of our covariates are binary, the mean is actually just the prevalence or the probability of the proportion of the people with that variable, and then we divide that difference by the standard deviation of that variable. And so the plot that you're getting when you compute the covariate balance and then plot covariate balance scatter plot is this plot, where on the x-axis you get the standardized difference of mean before matching, and on the y-axis it's after matching. If the matching had no effect, everything would be on the diagonal, but you see that the matching does have an effect, and in this case, a good effect in that there was quite a large amount still of imbalance on some of the covariates. As you can see, these things were very unbalanced before, and then we did the matching and it reduced the covariate balance significantly. And we use, again, it's a rule of thumb, so don't get too caught up in this, but we use a rule of thumb that after matching you want to be below the 10% line, the 0.1 line. And so here we see that all of these variables are below that. And Graham even said that a standardized mean difference smaller than 0.1 indicates a negligible difference. And so that's what we also see.
He was just repeating us.
Yes. That's funny how that just starts with one person saying it and everybody just copies it. And here I am copying it again.
So,
Yep, go ahead.
See if I'm understanding this. So, before standardization, they would all be right on the line, right?
Before matching.
Before matching, right. In order to get them off the line, you're just getting rid of some things. Like, you've matched, but the reason the mean changes is because you've thrown things away as a result of matching, right?
It's two things. One is you've thrown people away, in this case with matching, but also you've imposed a stratification. Every matched pair in this case is also considered to be its own strata. And so that's also taken into account when computing these numbers.
So the whole mean may still be different, but within the strata, the means are the same, are a lot closer.
Yes, that's it, yeah. And so in this case, because both things are going on at the same time, it's hard to tease those apart. But if you do stratification, it's very obvious because you didn't lose anybody, but you did now impose these strata. And so your mean can actually change, and certainly the standard deviation changes. Or the mean can change, but the standard deviation changes. And so the difference, the absolute standardized difference of mean does change because of the stratification, quite a lot usually.
If you just did the stratification and then showed the difference, so you have a standardized difference of mean after stratification, but then you have another one after the matching and throwing people away, you could draw those. I'm just wondering, would it be interesting to anybody to know what effect is coming from which of those operations? No?
You're just interested in did I achieve balance afterwards?
Okay, right.
Yeah, I don't even know how you would. Oh, you could even do that. You could just, in this case, I could go into that object, match pop, and I could throw away the strata, and I would actually probably works without any glitch. Yeah, probably would give you the effect of just throwing away the people, and then you could run it again with that stratum ID column in there, and then you would get it with both. So, but I don't know anybody that's ever looked at that.
Clarify, the strata part is editing matching without conditioning.
Yeah, so this is a bit tricky to explain, so I'm not doing a good job, I guess. So there are some that just do matching, like one-on-one matching, and then they just then consider it to be the population that they do their analysis on, and they don't think about the matched set that they've just created. What we typically do is we actually say, no, they're now stratified, and each matched set is a strata of exactly two people, one in the target, one in the comparator cohort. And when I do for example, my Cox regression, I'm actually going to condition that on the strata. And I think that is the nicest thing to do, because you're taking into account the stratified nature of the data. It does mean you lose some power. So there is an option also to not use the strata when fitting the Cox model, but
I mean, it affects the outcome model, condition or non-condition.
That's right. So in the outcome model, you can choose to condition on the strata or not, and in this case, the strata are the matched sets. And so if you do propensity score stratification, you have to condition on the strata, because else your propensity score has no effect at all. In this case, you have an option, and I've seen people that don't do the conditioning, and I see people that do it. So we're in the camp that does do it, but it really is a question of, again, looking at the diagnostic, what works best. But we just have a preference for doing the conditioning.
But you're saying that it can do standardized mean difference with and without conditioning? Is that what you?
Oh, that was just an answer to Siegfried's question. Usually just look at the effect of both.
And I don't know
But
how these things work, so I'm just asking questions to get a feel for.
To your point, if you're not going to do conditioning, so in the case of one-on-one matching, it's actually, in theory, okay to not do the conditioning. If you're doing variable ratio matching, it's pretty much the same as stratification, in that if you don't do it, you're not using the propensity score. But if you're just doing one-on-one matching, it might actually be okay to also look at what the balance is without that stratification. I just haven't done that, but like I said, this object, this matched pop, is just an R data frame, and it has a column called stratum ID. If you just set it to null and you feed it into this function, I'm pretty sure it will just work, and you'll get the standardized difference of mean just based on the fact that you threw away people that were not matched. And that's one of the nice things of flexibility when you're in an R package, is that you could write that R code yourself and just do that if you wanted to. Yes, people always invent ways of doing things differently than we had thought of, which is not good or bad. That's just what it is. All right, so Graham said Cox proportional hazard regression was used to compare time to event, etc. So that's what we'll use as well. So we'll set model type to Cox, when we call this fit outcome model function. And in fact, it was ambiguous in the Graham paper whether or not they applied this conditioning on the matched strata. Yep, I don't know. So I was assuming they did, but
I don't think they did either.
Oh, okay.
I think it's wrong not to, but I think it's quite standard to not realize that there's a difference.
Yes. All right. So in this case, I think we set it to false here as well. All right.
But this is also using our replication of the covariates.
Yes. Anyway, so once we fitted the outcome model using that fit outcome model function.
That'd be interesting. Yeah, I'll be surprised. My understanding that we use conditional Cox model. So since you run the did a one-to-one matching,
You can do both.
you could actually run the result, just see how different they are, right?
Sure, yeah. So you're perfectly welcome to run a sensitivity analysis, for example, and
And let
just
me know.
see what that makes a difference. Yeah, that's fair game. But we're not going to do that now. So once we fitted our outcome model, we can call summary on that R object, just as any other R object. And so then we get this result, which is basically showing us the hazard ratio estimate with its 95% confidence interval. How many people we had in both groups, how many days were observed, and how many people actually had the outcome in both groups. So using that information, the number of people that had the outcome, so this is outcome counts. So that's telling you how many people in one cohort and how many people in the other had the outcome. And we know how many days they were observed in both groups, so taking into account the time at risk definition. Yep, go ahead.
Shouldn't the counts be the same for treated and comparator if you have a one-to-one?
No, so this is the number of outcomes. So we did one-on-one matching, so we know the number of people is actually the same. So yep.
Yeah, that's up there, okay.
Sorry, yeah. The number of people is exactly the same, but the number of outcomes sure doesn't have to be, and certainly the number of days also doesn't have to be the same because some could be observed longer than others, and we didn't match on that. So what we observe here is that the Bickerton group actually had more outcomes, but they also had more time at risk. And so if you compute the incidence rates, you see that actually the incidence rate in the Bickerton group was lower than in the Worfen group. And actually they're fairly similar to what were, in this case, in this reproduction, they were very closely aligned to what was reported in the Graham study. We can also call the plot Kaplan Meier function on the matched population. And so we see this Kaplan Meier curve. We like to see confidence intervals in our Kaplan Meier curves, and I know that Graham apparently does not, or he doesn't know how to compute them. But I think this is much more informative than this, because this seems to suggest, oh, there is a large difference between these two groups. This tells you, I don't know about that. Anyway, so the execution steps in such a cohort method study is getting the necessary data, defining the study population, creating a propensity model, and then doing matching or stratification or whatever. And then fitting the outcome model, and in between there you can take all these extra steps to generate the various diagnostics. And of course you can leave steps out. If you're not going to do matching, you don't have to do propensity model. Alright, so that's the nuts and bolts of what it looks like if you did it all in R. But we've created this Atlas tool that means you don't really have to unless you want to do something different. So when Jamie clicked on that button, what I did is in the back end it generated an R package. An R package is actually a unit of code, sometimes together with data, that can be sent around and can be installed on a specific machine. And it basically means that once you've installed it, you have a bunch of functions at your disposal. Just like the Cohort method is a package, the thing that was generated by Atlas is also a package. But it's a different package in that package is what we call a study package, and it executes a study. If we look at the anatomy of that package, what is inside the package is the following components. So we have some functions basically that you can call. So these are what I would call the execution code. So there's the main execution code, and actually there is a function called execute. And that's usually the only function that you're interested in because that executes the full study. There's also a function that launches a Shiny app, and I will show you that later, that will allow you to inspect the results once you've executed the study. But there are more inside this package. There's some payload brought along. And first of all, there are the cohorts that you define. So your T, your C, and your O cohorts, they're actually inside of the package now. They're both inside both as a JSON definition. So there's just a JSON file for every cohort that you define. And so that's there more for reference, that later on, if you dive into the package, you want to see which cohort definition was used, you can pick up the JSON, plug it into an Atlas instance, and you have exactly that definition. But also there is the SQL definition. So Atlas turned it into SQL that can be run against any CDM database. The nice thing about having that inside of the study package is that even though Cohort Method itself doesn't know how to construct cohorts, the study package does. So if you go execute on a particular machine that's connected to the common data model, what it will do is it will actually construct your T and C cohort at that site. So that means you can just send it to a completely different site, say, whoa, run execute, and on that side, magically you will have the T, C, and O cohort instantiated and ready for use for the Cohort Method package. If you specify negative controls, then inside the package you will find the negative control concepts, and as I said, you need some sort of a way to turn a concept into a cohort. That is a SQL template that will be also inside of the package. You define positive controls, there are some settings for that. And then there are the analysis settings. So there's a definition of, well, which one of these cohorts that we just created is the T, the C, and the O, and which T's and C's and O's are we actually going to be comparing. And then there is these analysis definitions. So that's basically a list of these analysis objects that I referred to earlier. That for every one of the functions that we probably want to call in sequence, it tells you which arguments should be used for that. So this is a full self-contained unit that's just a study that calls the Cohort Method package. And like I said, you just run execute at a site, it instantiates the cohorts, it instantiates any negative controls if you want, it generates positive controls if you specify that, and then it runs Cohort Method at the multiple analysis level using these objects and basically generates all of the results that you're interested in. So if you want to know specifically where all these objects live, I've identified the folders inside of the package where you can find these.
Oh, can you go back?
Yep.
So all of these are customized to your study.
Well, so this bit on the left is actually generic to any
Oh,
study.
that's generic.
But that's specific to your study, yes.
Okay, so wait, I'm seeing that there's some stuff in my R directory that has the name of my study in it.
Yeah, so what we do is we just do a find and replace for some generic name that we had and replace it with your study name that you defined.
So
but it's the same code that would be anywhere else. It's
you
just,
didn't change the code, you just threw the word in there.
yeah.
Can I spur a question?
Sure.
What happens if the definition of your outcome of interest is wildly different than the definition the generic definition for your negative control outcomes?
Yeah, so that is a question that we have is how comparable should your outcome, your negative control outcomes be to your outcome of interest? If your outcome of interest is something that's only observed in an inpatient setting or in an emergency room and your negative controls are any occurrence of a code, I would say your negative controls are still valuable in measuring some types of systematic error, but not maybe some of the systematic error that is specific to the setting in which only your outcome of interest occurs.
Is there any value in using the identical instructions that you use to define your outcome of interest, but just swapping that out with the concepts for the negative controls rather than this more generic approach?
Well, so we thought about things like that, but like an ingrown toenail, I'm not going to have a primary diagnosis in the
You need 3 of them on 3 separate visits in order to have it. Right.
Yeah, so, well, you could think about that, but so certainly, but this is what we usually use, but you're certainly free to use another template here. But we just try to provide the one that we think is most appropriate in most settings. Yep.
I'm just looking in the inst settings directory, and the names of the files are not obviously associated with things up there. Like analysis definitions, is that CMA analysis list?
Yes, so CM analysis list is the combination of these objects.
Oh, okay. All right.
Yeah, maybe I should have actually put the actual, I tried to put the actual names up there, but it just, the slide got a bit
Got it.
cluttered.
So how big is a typical study package, like for the grammar one?
Just a bunch of kilobytes.
50, I'm guessing.
Let me see, I added here in my download.
Probably pretty small, but.
Yeah, it's pretty small because it's just code. It's just not any data. So this is 125 kilobytes.
Yeah, I mean, but that's an irrelevant quantity.
Yeah, no,
That's not anything that it has.
And then the other question is, how big is 17,000 data, 7,000 patients worth of Medicare data?
Those are gigabytes.
No, not
I'm
data.
just trying to understand how big of a machine do I actually need to run this in a reasonable amount of time?
Right. Not that big actually. The code is pretty efficient, I would have to say.
So, frame of reference, I use this package on my laptop.
Yeah.
I sometimes complain that it takes a few hours, but it always finishes.
Sure.
Legend would not finish, I thought.
Yeah, I would not do Legend on my laptop.
All right, so the big question, of course, is then how do we install this? And so there are a couple of ways in which you can install this package that we just downloaded, which is just in a zip file. There are basically two ways. One is you can use RStudio and build and run it there. First step would be to basically open up the package. And there are two flavors there. If you're using your own machine, you just unzip the zip file, and in it you'll find a file with the rproj extension. You just double click that, and that will automatically open up RStudio for you, and you're in your R package. What I'll show you here is, because we have this fancy Amazon environment, how you do that in the Amazon environment. So you should have that open up here. So the thing to do there is, let's first create a folder where I want to unzip my package. Call this Graham test. Right. Go to that folder, and then I click on upload, and it already is set up. That's a default R server feature. That will allow you to point to a zip file. So this is actually, I also downloaded it on my machine. So this is the zip file that Atlas created. I just click on open. Okay. Now it will load it and unzip it for me, and I have the package here. So I can just click on the rproj file. I want to open that. I don't want to save my workspace. So here I have the package. So the next step is I need to actually install the package. I've just opened it. And so in RStudio, you go to build, you click on install restart. We get an error. Sorry, I was too fast. An R package usually has dependencies. You need to have other packages installed to install this package. And of course, your study package has at least a dependency on Cohort Method, but it has other dependencies as well. But to make life easier, I've created this README file here that actually tells you what you need to install. And so there are some instructions here on how to install all of the dependencies. So I actually have to do that before I go any further. That's annoying. Sorry, I should have done that beforehand. But I think they completely rebooted the Amazon environment before. I'm just going to hit run on that. That should hopefully just work. So what that will do is it will get all of these packages from GitHub and install them in this machine. Let's hope there are no errors.
So I ran the estimation on my machine. I just made one and ran it. But did you guys send this out so we all have a copy of this zip file, or?
No, we did not.
Oh, okay. So if we want to see one, we have to have run it ourselves.
Well, no, so you can now, you all have access to this Atlas instance. So what Jamie just did, you can do too. So this is the Atlas in AD. Do we have it here?
Yeah.
So we go to estimation.
Is there one already on
There should be already one. There it is. So we click on that one, and then you just
there? And download.
just download it. So
Got it.
you can now. All right. So I'm done installing all of the dependencies. And so, of course, if you were to send this package to any other site, you would have to point them to this README file and say, hey, follow the instructions here to run it. And so now I've installed the dependencies, and now I'm going to click on install and restart. And so that will work just fine. Wow, this environment is fast. All right, so now I've installed the package. Another way to install the package is by using GitHub. And so specifically when you're in a OHDSI network study setting, that is probably the way that you'll deploy this package. You'll unzip it, you'll put it in a GitHub repo, and then it will just look like you could put it into a study protocol sandbox, and then the README file will actually very nicely pop up as the front page for that repository. You can point other people to that location, and then what you can do is you can use install GitHub to install that package from GitHub directly onto your R instance. But both are equally valid ways of installing the package. So as I already mentioned, there's in the README file there is some code that you need to run to install all of the dependencies. And then the next step is running the package. And actually there is also in the README file the instructions on how to run the package. So you need to load the library. You need to set a bunch of settings, like setting the temporary directory where very large data objects are temporarily stored is a good idea. So you need to make sure also that a folder exists. The number of cores that you want to use. So as I mentioned earlier, if you're going to fit a very large propensity model, that's going to take a while. And so if you have 4 cores in your laptop, which you usually have, I would set max cores to 4, or actually this parallel detect cores command already detects how many cores you have. So you could also use that, but maybe you don't want to use all of the cores in your machine because then there are none left for other stuff. Min cell count. So at the end of it, what the package will do is it will put all of your results in a zip file so you can actually share them with other people. But maybe you don't want small cell counts to come across. Like if you have only one person with the outcome in your target cohort, it might be that you actually have rules or regulations that prohibit you from reporting that one cell count because that uniquely identifies a person, even though you don't really know that much about it, but rules are rules. So here you can set the minimum cell count that should be in that data export that you might want to share with others. The output folder where you want to store it, connection details, where the database is. Let's see if there is anything else of interest here. Nope. All right, so then the final thing in the README file that I didn't have in my slide is you call this execute function that I mentioned earlier. So that just has all of these things, how to connect to the database. And it also, you have some options for which steps to run, although I recommend running all of them. But this is more like if your computer crashes somewhere halfway through run diagnostics, you don't have to run everything before that. Again, you can just set those to false and run it again. But basically, you want to leave that to true. And if you call that execute function, it may take a while. Like I said, it's going to create the cohorts on the server. It's going to fetch all the data, create all the covariates. It's going to fit the propensity model, maybe multiple times if you specified many TCOs and whatnot. But in the end, it's going to fit the models and produce all of the results. And create an export. So the export that it creates, it's all CSV files, but it follows a structure that is defined here. So we call this we don't actually have a name for it.
The results model.
Yeah, the cohort method results model, or whatever. We don't have a name yet for it, but basically we tried very hard to think of what kind of data do you want to share with others, and what do the others actually need, for example, to create plots. And so we came up with this data model, and that is the data that's being exported. You can go to that link to get a full description of the data model and what all of these fields mean. What is important to realize here is that the data here it's all aggregated data, so these are all results. There's no patient level data here. We have this minimum cell count that I mentioned earlier that's being enforced. We save all this as CSV files, not because we've never heard of our data objects, but because CSV files are very easy to review, and you know that you're not sharing more information that you think you're sharing. And we do zip them for convenience, but basically the whole idea is that this object is something that people can inspect to make sure that they're not sharing stuff with you that they don't want to share. And they can look at the data model, etc. And so if you're doing a network study, it should be okay for everybody to share these exports with you. Even though it's very rich data, you can do nice things with that, as I'll show later on. So once you have that export, you can launch the Shiny app. You don't have to. You can also just analyze the data by yourself. You just need to call two other functions that are in the study package that you just downloaded. Prepare for Evidence Explorer, because Evidence Explorer is the name of our Shiny app. And so you point it to the zip file that was created, which could be a zip file that you received from some other site. And you need to point it to some data folder. So if you have multiple sites that contribute to data, you just call this command over and over again, so that from every data site it reads the zip file and puts all the data in that same Shiny data folder. And then you call Launch Evidence Explorer. There is an option that I think is a pretty important option. It's called blind. So one of the things we firmly believe is that it's bad to do p-hacking. Meaning you shouldn't change your result based on the results, change your design based on the results that you observe. However, it is totally fair game to change your design of your study based on your diagnostics. So if you have your propensity score distribution, your covariate balance, you have your negative and positive controls and the estimates for those, and you see that your study is bad, it's very biased, at that time it's still okay to go back and say, oh, maybe I need to do matching instead of stratification, or maybe I should remove some covariates or do something else. And so if you set blind to true, what that does is for the outcomes of interest, it hides the results from you in this app. So I know they're already computed and they're sitting in CSV files, so we're a bit on the honor system here that you're not going to look at them. But if you're being honest, you can set it to blind to true, and you can look at all these results and see whether or not what you produce is actually looks like a good study before you set blind to false, and you're actually unblinding yourself to the actual results. So let me show you what the Shiny app looks like. I'm going to do that on my laptop just because I don't know how the Shiny app is going to look in the Amazon environment, but I'm probably okay with running it there. So I ran this package on our J&J data. So I'm going to launch the Shiny app. I've turned blinding off, so I'm actually going to see the results. I'm actually going to open this in the browser. Maybe I can zoom in a bit here. Or whatever. For those of you who were at my presentation yesterday, it actually will look pretty familiar because it's just the same idea that we use in Legend. So here is the data that came out of the study. So I can choose my targets and I choose my comparator. In this case, I only had one, and I can choose the outcome. I think I only also had one. I only ran it on one data source, Medicare, and I only have one analysis to look at, but could have many. And so for the choices that are defined on the left, on the right-hand side, I see the results. So for the primary analysis in the Medicare database, I now have a hazard ratio with a 95% confidence interval and p-value, and I have, in this case, because I turned positive control synthesis on, I also have a calibrated hazard ratio and 95% confidence interval, and I had negative control, so I had a calibrated p-value. And I can click on that. So now, like I said, all the data that was in that data model that I showed you earlier is exposed through the Shiny app. So I see how many subjects were in T and in C, how many years they were observed, how many events were observed. Here is a power calculation, so what was the minimum detectable risk given those numbers. And here we get a distribution of the follow-up time. what was the minimum follow-up time, or just 1 day, because we require at least 1 day of follow-up, what's the median and what's the max, etc. We can generate the attrition diagram. So like I said, you can also, if you're just at the single study layer, you can also call this function yourself, but here it is shown in the Shiny app. And if you think I want to use that in my, my paper, I just click download diagram and I can download this as an image file. Population characteristics, so there's actually a file that drives, yep?
Question.
Sure.
Regarding the line of code, is it possible to run this propensity score diagnostic data without the outcome at all and just see the diagnostics in this app? Or maybe it's possible to, for some people, not allow access to anything related to the outcome?
I don't think, I certainly haven't tested that, so I don't think that's going to work if you have absolutely no outcome.
I would suggest changing your outcome to something you don't care about.
Yeah, just.
And then to run the whole study with a bogus outcome. And all of these statistics will be the same. They're not dependent on what your true outcome is. And then it's safe to share that.
I actually have done that. I've done that myself once when I wanted to be absolute clear. What I did was I actually took one of my negative controls and made it my outcome. And that way the only thing in there was actually a negative control. There is one slight caveat though, which is, which Martin went through. Specifically the outcome based on the parameters might influence the population a little bit. For example, you may exclude people who had the outcome previously. And so from that perspective, if that matters, you actually do need the outcome. You need the real outcome to make sure that you're really getting the exact people you want to do the analysis on. So,
but you only need that for the exclude prior event.
There's a pathway through it where you wouldn't be worried about that, but
it's inconvenient.
More times than not, you would actually want that using the real outcome to play exactly it.
But certainly, if you're running Cohort method at just the single study level, so really just calling commands. I mean, there's nothing saying you can't just stop after you say create PS, but then you can't use all these fancy features that are in the study package.
We should think about some more secure blending.
Yeah, sure, yeah.
I mean, I'm just wondering if this sponsor, you don't want them at all to look at the outcome, so
Okay, yeah. Yeah, we need to look at that.
So we can always throw in an option that they don't get packaged up.
Well, but yeah, I think you have to draw a distinction between who has programmatic access to the data and who can only view results. Right now you're learning how to run code. That code requires access to touch the data. So if someone has permission to touch the data, they can the tool cannot prevent them from looking at the outcome. The moment they can write an SQL query, they can look at the outcome. But there is the possibility that you could prevent someone from actually having access to the data and only give them access to the Shiny viewer, in which case they would not be able to see anything. And that would be fair game. But you could actually, at that point, you could just give someone the thing without the data file of the outcome.
Yep.
So you give them line equals true, and that becomes your output.
So another tab shows you population characteristics. And so here what we did is we just selected some of the covariates that were generated when you set the defaults on. Not all, because it's hard to show 10,000 variables here. So we just picked some like the age groups, the gender, race if it's in the database, and some medical history. And so that will all be shown here. So what we're showing here is the percentage of people in the targeted comparator group that belong to that specific category, have that specific covariate, and the standardized difference of the mean, both before the propensity score adjustment, in this case one-on-one matching, and after the adjustment. You can also look at the propensity score distribution. We can look at the covariate balance. And so the nice thing about the Shiny app is that this is not just a static picture, but we can actually just mouse over things to see which ones are the covariates that are maybe still out of balance after matching. Well, everything is in balance, but You can look at that. I don't know why that is there. All right. Systematic error. So we didn't go into this in too much detail, but there's this notion of negative and positive control outcomes where we know what the true effect size is. And so in this case, we included both. We defined a set of negative control outcomes where we know that the hazard ratio should be 1. And we use this fancy technique to synthesize positive controls from those negative controls, in this case with a true hazard ratio of 1.5, 2, and 4. And then in the top row we see whether this method that we're using and we're applying for the outcome of interest, how that looks for all of these negative and positive controls. And we see that those estimates actually, they should be within these red dashed lines, or at least 95% of them should be. We see that that's pretty reasonably very close. So instead of 90%, 95%, it's 90% here, 81% here, and so it's a little bit low. So we can use this notion of confidence interval calibration to correct that, and so we see we get much closer to the nominal 95% that we would like to see. So that's just, if you're looking at this calibrated confidence interval you see up here, then these are the operating characteristics for that confidence interval. If you're looking at the uncalibrated ones, then you know that, for example, if the true hazard ratio is 4, then the truth is actually going to be inside of the 95% confidence interval only 75% of the time. So that might not, you can keep that in the back of your head. And here's the Kaplan Meier plot. And in this case, we didn't look at any interaction, so the subgroup tab will actually be empty. And I think that was pretty much what I had prepared. Yeah, so the Cohort method package plus R are for large flexibility. So the reason why we build all this in R to begin with is to allow for this flexibility. And so if you have very specific questions that we didn't think of, you can just write your own bit of R code to do that. I would expect that 80% of the studies that people want to do, you can do with Atlas, because it's like a cookie cutter design study. I also expect that for 20% of the studies that people want to do, it's probably not going to be flexible enough. You actually have to go down into the nuts and bolts of the R underneath to get what you want. And so in that case, you could use the code that is generated by Atlas as your starting point and then develop from there onwards. All right, that's what I had. Are there any more questions?
Can we also look at the reading data on your Shiny app? I saw you had both outcomes selected for the exercise. Can we look at the reading data?
No, so that was what Jamie had done on that end, but that was not what I'd run.
Okay.
All right, and then it's time, I think, for Patrick, right?
All right, you're supposed to get a little brief.
All right, is that?
Like, please don't let Patrick get up there.
Oh, you're right. Oh, you got a short break before you're exposed to Patrick. So. All right, we had a 15-minute break.
It's actually good to ask for.
No long exposure to Patrick may cause that.
Actually, I was just about to take off, and now Patrick may take a personal accident.